This video introduces the extrema of a functions on an interval. So what are extrema of a functions? Extrema or a point are the absolute maximum value or the absolute minimum values of the functions. And they also can be called at, global maximum value or the global minimum values. So the global maximum value is a point of the functions on an interval where it's the largest value. And the global minimum, vice versa, is the smallest value of the functions on a specific interval. Well, let's look at a graph of the functions f of x. Okay, and then I can graph these functions, say, like that. Okay, and I want to consider these functions f of x on the interval from, let's say, 0, open interval from 0 to 10. Okay, and now we look at these functions like, oh, which one is the maximum value? Which value is the absolute maximum and which value is the absolute minimum value of this function? So now first let's look for the absolute maximum value of these functions. So if I look at using my eyes, right, I can see that, oh, this point right here could be the maximum value, the absolute maximum value, which is the highest value of the functions on the interval from 0 to 10. And again, we're looking at the open interval from 0 to 10, not the closed interval. Okay, so I guess maybe this point right here is the maximum value. So let's say f of 10 is the global maximum value. Okay. Well, I have to have a question mark there because I'm not sure, is it? First, f of 10 is not defined in the open interval that we're looking at, right? On 0 and 10. Okay. F of 10 is not defined because 10 is not included. So if f of 10 is not the global maximum, then can we guess that maybe a point that is very close to this point here is a maximum, absolute value maximum? So maybe this point? When if it's not f of 10, then f of 9.99. Okay, maybe, right? It's very, very close to 10. It looks like it's right here and it's in the open interval that we're looking at right now. But then another person is like 9.99. I want to go a little closer, which I will add another 9 here. Okay, well, it's closer, and it say that as you get closer to the point, to this point, f of 10, you have a higher value. So as you go closer, you go a little bit up in terms of your function values, right? And then another person is like, I want to get a little closer. I want to get another 9 there. So you can keep going. Like you can keep add more 9s into this guess just to achieve the global maximum value. If this is the case, then that means we don't have a maximum. We don't have a global maximum value. Because if we can just keep getting closer and closer and closer to f of 10, our values keep increasing, and we will never reach the maximum, the global maximum value. Okay. So that's being said, we don't have any global no global maximum value. How about global minimum values? Well, we're going to search for global minimum values, meaning we have to find the points where it's like the lowest, smallest value of a function. So again, we're starting from here. And we ended up here. Okay, and then looks like this is a point where, it's the lowest point of the functions on this interval. And stand here, I would say this point is 7. So you have f of 7. Okay, and it would say this is -1. So actually we found this is a point where it's like right in the bottom of this function's on this interval from 0 to 10. And this is the lowest value that we can find. And we actually could find that value is f of 7. And then we can assign it a value. It should be -1 here, right? So f of 7 equals to -1. And this is the point right here. What does it mean? That means we found a global minimum value. So f of 7 equals to -1 is the global minimum value of functions on the interval from 0 to 10. Okay, so for the conclusions, we don't have any global maximum, but we have a global minimum value on the interval from 0 to 10. And one thing that you can notice is, that at this point right here, at the minimum point, if you draw a tangent line at this minimum point, the slope of the tangent line here is actually just 0, right? Because it's the horizontal line. That means if you find the derivative of the functions, f, you plug the value 7 into the derivative, you will get 0 as the result. So this is give us an idea on how can we search for the global minimum or the global maximum values. We're searching the functions at this point where the derivative of the function equals to 0. So your extrema values might occur at one of these points, right? And you can see that you can see yourself that, okay, I have another point where the tangent lines is a horizontal line. So let's say if this point here is 2, then f prime of 2 also equals to 0. Okay. So you look at this point right here, it's not the absolute value of the functions on the interval from 0 to 10. However, it achieves a maximum point in a small interval. Okay, so in this interval right here, this point f of 2 is a maximum value on a small interval around it. Okay, and later on we'll learn that this point here is not the absolute value maximum, but it's gonna be the local, right? Local maximum value. And also we'll know that this point right here will be a local minimum value. This is a local minimum value, but in this case, in this particular specific interval, is the global or absolute minimum value. All right, and then you might wondering, okay, so now we search for extrema. That means we have to search for all the values at which the derivative equal to 0, or the values on, you know, the edge, the endpoint of the interval. How can we search for these values and this value? We need to use the derivative, right? And then you set a derivative equal to 0, we can find this 2 value right here. So finding the derivative is something that we have already learned. It's actually one thing that we learned in chapter 3, right? And then as you can see, the applications of the derivative is here. Searching for the local minimum or the global minimum or global maximum is searching for this point where the derivative equals to 0. So now if we know the function f of x, we can find the derivative f prime of x for sure, right? And then in order to find all of these like special points right here where extrema can occur, you can set f prime of x equals to 0 to find this point. All right. So there's a theorem on the extrema value. So the theorem says if a function f is continuous and on a closed interval, then f has both maximum and minimum value on the interval. You say both minimum and maximum, and these minimum maximums mean they are global or absolute minimum and absolute maximum value on the interval. And the reason is, so let's say if we have a functions, right? And you draw a graph of a functions, that. And I'm considering this graph f of x from 2 to 8 on a closed interval. Again, closed interval, not on an open interval. Then this theorem guarantees that we can find a global maximum and also a global minimum value of the function on this closed interval. All right, so what is the global maximum? So as you can see that this point right here, f of 2, right, is the global max value. All right, and at f of 6, well, this should be 2 to 8. So this should be around 5. F of 5 is the global minimum value. So we found the 2 extrema, global maximum and global minimum. If we given a function that is continuous on a closed interval, then make sure that you can find the 2 extrema values. Okay, absolute value of max and absolute value of minimum. All right. So now we can discuss, local maximum and local minimum and critical numbers. As we mentioned above here, these 2 values with 2 points at x equals to 2 and x equals to 7, these 2 points, here are the points where the derivative of the function equals to 0. And these are very special points for the functions in terms of this derivative. And these 2 points here are called the critical point of the function. Okay. So if you look at this function's f of x right here, you can see that I can find, oh, this point would have a horizontal tangent line. This point also have a horizontal tangent line, and this point is also have a horizontal tangent line. These 3 points here are called critical values of the functions f of x. All right. And you can see that they are critical values, and they have some special things about their positions, right? All of these 3 points are either local maximum value or local minimum value. So this point is the local max. This is local min. And this is local max, right? And by looking at the graph, we know they are maximum or minimum, because the reason why they have the name local maximum value or local minimum value is they are the maximum or the minimum value of the functions on an interval that is around them. So if you look at this local maximum here, if you look at this interval from this point to this point, right? So this point is the maximum, the highest value of the functions on this closed interval, the interval that surrounding this point. Similarly, if you look at the interval from this point to this point, then this point here is the smallest value of the functions in this small interval. Again, they are local, meaning they only have their meaning they are the maximum value or the minimum values on a very local area, similar to this point. So this is the maximum value on this closed interval, this small open interval right here. They are global, they are local values, local max or local min values. Doesn't mean that they are all gonna be global or absolute value, absolute maximum value. So if you have the functions, let's say if my function is keep going down this way, right, and then this function is keep going down this way, it goes down to in the negative infinity, then what does it mean? That means we found the 3 local extrema, right? The 3 local maximum or minimum value, but do we have any absolute maximum value and or absolute minimum value? So that's a question that we would like to answer. So let's look at the graph again. You can see that this point right here is the absolute maximum value, right? It's the highest point on the entire interval from negative infinity to positive infinity. No other values that is higher than this value everywhere. Okay. And also this is the local max. But then do we have an absolute minimum value? Probably not. So we have local min right here, but again, this is not the lowest value of the functions on the entire number line, right? You have like lower values down here, lower values down here. And as the functions goes down to negative infinity when x approach to negative infinity, and also go down to negative infinity when x approach to positive infinity, then you will never reach the lowest value. That means no absolute minimum value. Okay, so no absolute minimum value. And again, I just want to emphasize on, the difference between global extrema and local extrema. And in both cases, when you're trying to locate extrema value, it's very, very useful if you can find all the critical values, because most of the time, global or local extrema occur at those critical values. And the critical values, by the definitions, is a point C, right? Where f prime of C equals to 0, or f is not differentiable at C. So not differentiables mean when you find the derivative of f of x, f prime of x, and C is a point where f prime of x is not defined, right? F prime of C is not defined. That's what I mean when it's to say f is not differentiable at C. And C is a critical number if C satisfies these conditions or these conditions. All right, so now we know how to find critical values, find the derivative, and then set it equal to 0, and then solve for x, right? So here's another theorem that related to relative extrema or local extrema. I forgot to mention that local extrema has another name. It can be called relative extrema. So relative maximum, local maximum, relative minimum is the same as local minimum. All right. So the theorem says if f has a relative minimum or relative maximum at a point x equals to c, then c has to be a critical number of f. So if you can find a local max or local min value of the functions, then those points has to be one of the critical values of f. All right. Now we talked about earlier, remember we talked about, this theorem when you guarantee to have extrema value, right? Absolute or global maximum and global minimum value on a closed interval if the function is continuous on that closed interval. So the next question is, how do we find these two, value, global maximum and global minimum of a functions on a closed interval? So the answer is you will have to find critical values, right? This point. And then you also have to pay attention to the endpoint of this closed interval, because in this case, the absolute maximum value occurs at f of a, f of 2 occurs at this point. And the global maximum or global minimum of this function occurs as this is the critical value. So in order to locate the two absolute extrema, we need to first find critical values of function f on a to b, right? And it can be just open interval a and b, right? Just find critical values. And then you evaluate the function f at each of the critical number. So you find the value. And then you evaluate f at each of the endpoint, like f of a and f of b. Okay. And then you compare all of these function values together, the value of the function at critical values and the values of functions at the two endpoints. And then you can make the conclusion. So the least of the values will be the minimum, and the greatest will be the maximum value. Okay, find all the critical value, evaluate those functions at those values. Also evaluate the function at one of each endpoint, and just compare them and find the least number and the greatest number to be the absolute maximum and the absolute minimum value. Okay, let's look at an example. So we want, so for each of the functions, explain why each of a function has both extrema values and find those extrema values. All right. So first we look at this function is a polynomial functions, right? We know that f of x is continuous on the closed interval from -1 to 2. Then by the extrema value theorem, f of x has both extrema values. By the on the closed interval, right? On the closed intervals, and we know that there's two of them, two values. So the reason why we have to make sure that the two extrema values exist is, you know, most of the times, all the time, before trying to find something, you want to make sure that that thing exists. It's always faster and it's always better to know that something that we are finding exists somewhere. Okay, so that's the first thing. And the second thing is we have to find them. So we're following the step. So first, find critical value or critical numbers, right? How to find critical numbers? We need to find the derivative of f. F prime of x. So f prime of x is 12x cubed minus 12x squared. And then next step is we going to set f prime of x equals to 0 to find critical numbers, meaning 12x cubed minus 12x squared equals to 0, meaning I'm gonna put it down here. 12x squared, x minus 1 equals to 0, meaning x equals to 0 and x equals to 1 are two critical values. Okay, so these are the points where the f prime of x equal to 0. But by the definitions, critical numbers can be points where, you know, f prime of x equals to 0 or f prime of x is not defined. And luckily, this is a polynomial functions. The f prime of x here is a polynomial functions. It's defined everywhere. So we don't have any points where the derivative is undefined. That means the two critical values are just x of 0 and x equals 1. Okay, so what is the next step? The next step is I want to create a table, because I'm going to evaluate the function f at each of the critical numbers and evaluate the function f as the two endpoints. So in order to do that, it makes more sense to me to create a table. Okay, so first, critical values, numbers, 0 and 2, 1. Endpoint, -1 and 2. Okay, so I set up this table. And I plug the 0, all these values here, into the functions f of x. Remember, you plug all of this value into the function at f of x. All right. So if x equals to 0, f of x is simple enough, it's going to be just 0. If f of x is 1, then you have 1 to the 4th, and it's 1, 3 times 1 is 4, minus 1 minus 4 times 1 is just -1. If x is -1, then -1 to the 4th is 1. So 3 times 1 is 3, And then -1 to the third is -1 minus -4 is 4. So 3 plus 4 is 7. Oh, 2. 2, if you plug 2 into the f of x, you will have 3 times 2 to the fourth, which is 3 times 16, and minus 4 times 2 to the third, which is 4 times 8 is 32. So the answer is calculated it. The answer is 16. 3 times 16, 48 minus 30, 48 minus 32. So it's going to be 16. Okay. So if you look at these tables here, you can identify right away which value is the absolute maximum value and which is the absolute minimum value. -1, absolute min, right? 16, absolute max. Okay, and when you answer this question, you can say, you know, f of x has the absolute value when x equals to 1, and absolute minimum value when x equals to 1, and the absolute minimum value is actually -1. So the value is -1 and it occurs at x equals to 1. Similarly, the function has the absolute maximum value of 16 and it occurs at 2, x equals to 2. And again, we're looking at these functions on the closed interval from -1 to 2. All right, let's go to the next question. So you have another functions, right? And you want to see if this functions here is actually has both extrema values. So the functions 3, and you see that 3 f of x, there's no restrictions for the input value of x, meaning the domain of these functions here is all the real value from -infinity to -infinity to +infinity, meaning the function f of x is continuous, right? Everywhere, especially continuous on this closed interval. So f of x has both extrema value. Okay, now just go find it. It's the goal. So critical numbers. So we have to find f prime of x. So f prime of x equals to 3 times 2 over 3 x to the -1/3 minus 2. So this is going to be gone, equals to x -1/3 minus 2. Okay, and it's going to be, and you let f prime of x equals to 0, meaning 2 x -1/3 minus 1 equals to 0, meaning, you know, x to the -1/3 equals to 1, right? Meaning if you raise both sides by -3, then you will have, then you solve for x again. You want to solve for x and you will have the exponents here, then you raise both sides by -3 to have and this is -3. You know, 1's raised to -3, just 1/1/3. So it's just 1, so then x equals to 1. So x equals to 1, by the definitions of critical numbers, it's a critical numbers, right? But is it the only one? The answer is no, because if you look at the f prime of x here, so this f prime of x here, actually, you can rewrite it as 2 over x 1/3. When you bring negative x to the -1/3 down to the denominator, it will change to the positive, right? But it's go down to the denominator, not -2. And if you have x in the denominator, then you have a point where the f prime of x is undefined. So f prime of x is undefined when x equals to 0. So pay attention to where the derivative function is undefined as well when you finding critical numbers, right? Once you locate all the critical numbers, then your next step is very simple. You just need to create a table. So you have x, you have f of x. So x here, so you have putting 1, 0 as critical numbers. And then you put -1 and 1, right? The two endpoints of the interval. And then you just evaluate this value. Okay. So I just want to make sure that you understand that these two values, 0 and 1, are both critical number. Let me calculate these values real quick. Again, you plug it in the original functions, f of x, not the derivative functions. Okay. So f of 0, f of 1 will be 1. F of 0 will be 0. F of -1 will be 5. What does that tell you? That tells you this is the absolute min, right? And this is the absolute max. Okay, so we found, so the absolute minimum value is 0 and it occurs as x equals to 0. Absolute maximum value is 5 and it occurs at x equals to -1. So if we miss the point, this critical value, then your answer would be wrong, right? If you didn't pay attention to where the derivative of f of x is undefined to find the critical numbers, then your answer could be wrong. All right, next one. So you have these functions and arctangent of x squared, right? First, we want to know whether arctangent of x squared is continuous on the interval from -2 to 1 or not. So luckily, the function's arctangent of x squared is continuous everywhere. Okay, that means it's continuous on the interval from -2 to 1. First, the function f of x is continuous on the closed interval. So then f of x has both extrema values. Okay, now again, we just need to, find the critical values. Critical numbers. First, finding f prime of x equals to the derivative of arc tangent of u equals to u prime, and u is x squared, so u prime is 2x, and then divided by 1 minus x, 1 minus u squared, right? And u is x, x squared is x to the 4th. All right, then the next thing is you want to set f prime of x equals to 0, meaning 2x over 1 minus x to the 4th equal to 0, meaning x equals to 0. But again, we have to pay attention to the undefined value, like the points where f prime of x is undefined, and as you can see it here, x equals to 1 and -1. So f of x, f prime of x is undefined. When what? Does it have any value where the f prime of x is undefined? At first, I think yes, but actually, I made a mistake here. So the derivative of the arc tangent of x, arc tangent of u, equals to u prime over 1 plus u squared. Okay, and then u is x squared, so it's 2x over 1 plus x to the 4th. So that was my small mistake there. And you can see that it's very dangerous if you make a mistake, an algebra mistake, or a mistake during the process. That would kill your problem. Okay, now we're on the right track. So we don't have any points where the function f of f is undefined. Then x equals to 0 is the only critical value. Okay, so if this is the only critical values, then we will make a table and to complete this problem. So x, f of x, we have -2, 1, and 0. Okay, and then you plug your values into the arctan of x squared. So arctan of 0 is 0 because tangents arctan of 0 should be 0, right? Because the tangent of 0 is 0. You have it here. What is arctan of 1 on the interval from -2 to 1? Is it square root of 2 over 2? Arctangent of 1. And arctangent of 1 square. Yeah, I calculated it. It's gonna be 0.785. And arctangent of -2 is gonna be 1.508. All right, so I calculated this value, these three values, x and f of x, and then I can see right away, right, which one is the absolute value and which one is the absolute max and absolute mean. So this should be absolute mean, and this is the absolute max value. And if you want to make a conclusions about the two extrema values, this is what you can say. Say that now f of x has the absolute maximum value of 1.508 at x equals to -2. Okay, on the closed interval from -2 to 1, and f of x has the absolute minimum value of 0 at x equals to 0 on closed interval from -2 to 1. So this is how we're gonna locate the extrema values of a function on a closed interval following this 3 steps process, right? Finding, first you have to make sure that the function has both extrema values on a closed interval by making sure that the function is continuous on that closed interval. Then you find all the critical values, or the values where the derivative equal to 0 or the derivative is undefined. And then you make a table, evaluate all the critical values and the two endpoints of the closed interval in order to determine the absolute maximum and the absolute minimum values of a function on the closed interval. So again, this is the very first applications, one of the first applications of the derivative. And the derivative helps us find the extrema value of the functions. Could be absolute extrema values, or could be relative, extrema values. Could be global maximum, global minimum, or it could be global, local, or relative maximum, or local relative minimum. And those points, most of the time, occur at critical values. So when then finding the derivative set equal to 0 is when you find the critical values, and also find the points where the derivative functions is undefined. It's also where you can find critical numbers. All right, here you have it, extrema value of a functions.